Hello everyone and welcome back. We still have 5 minutes before the official class start time. So first of all, can you hear me? Good, thank you. So since we have a few minutes, does anybody have any questions for me? Either about the stuff we talked about last class or anything else, basically anything related to this class. Yeah, hopefully the T-Rex won't be visiting us today. No, we're not using Python. This course is entirely in Java. Not because I particularly like Java or because it's a particularly good language for what we're doing, although probably a little bit better than Python. It's just that because we want to do automated grading, we have to pick some language, and Java is the one we settled on. So hopefully you all have some experience from 1406. In general, we try not to fight with the advanced language features of Java. That's not the point of this course. Really, the course is about understanding the concepts. Java is just what we happen to use for implementations. And the assignments will be set up to mostly hide any ugly Java issues that creep up. Okay, so does a priority queue always remove the smallest item, or does it depend on the implementation? So a priority queue removes the smallest item, but smallest here means that it's always defined in terms of this compare to function, or the comparator that's being used in a priority queue. So if you have your own version of smallest, you can set up a priority queue with your own comparator that compares things the way you want. Just make sure that the comparator sets it up so that the thing that you want to come out next is the smallest thing. We'll talk a little bit about custom comparators when we do a bit of programming later. In the assignment question 3, it says in the order they appear. Does that mean the first line outputted is the first input line? Let me just look at question 3 again, because there's 10 questions. I don't remember what they all mean, but I think that's what that means. Yes, so in question 3 it says you're supposed to output the last 500 lines that that are in the input. So that means that the first thing that should be output is line, let's say, n minus 5,000. And then everything after that up to the last line of the input file. Good. Any other questions before we start? Okay, so we'll pick up where we left off last class. Last class we were looking at the interfaces that are included with the Java Collections framework. In particular, we were working on this part of the interface hierarchy here. We talked about collection, which is just the generic thing that all of these belong to. They don't do much, except you can ask them for their size, and you can iterate over them. That's about the only operations that I would use on something if you only know that it's a collection. We talked about sets. These are sets in the mathematical sense, unordered collection of distinct objects. Remember, sets were good for three operations: adding things to the set, removing things from the set, and checking if something is in the set. But they're not great if you care about order at all, because there's no notion of order in a set. If you happen to iterate over a set, you don't really know what order things are going to come out in. And then sorted sets were a version of sets that maintain sorted order on the elements in the set. And here sorted order means that things in the set are, if they're comparable, meaning they implement the compare to method. So that's all the standard basic data types in Java: integer, float, string. All of those things have a compare to method. Then you can imagine that they're stored internally in that order. And the most important thing there is that if you iterate over them, they come out in sorted order. And you can ask these sort of range queries. You can ask for a head set, which is everything up to a particular value, a tail set, which is everything starting from a particular value until the maximum largest value, and there's even a subset, which gives you everything in a particular range from a starting point to a stopping point. So that's sorted sets. Lists are a completely different beast. They are sequences. The closest thing that you've seen probably, well actually if you've done Python you've seen something called a list, which is exactly the same type of thing. Objects it's a sequence of things, indexed from position 0 all the way up to n-1 if there's n elements in the list, and you can access them by this index. You can add things, remove things, and you can change the values at specific indices in the list, or check the value at a specific index. Queue, we saw this is one that causes some confusion because people are used to queue meaning a first in, first out queue, that's the sort of standard queuing discipline, and very often in computer science when people say queue, that's what they're referring to. Here this is a more generic thing. This is just a data structure that lets you add things and lets you remove things, but you don't get to specify what gets removed. What gets removed is decided by the queuing discipline, and sort of the two common ones are first in, first out. That's where it's exactly what people are used to. Things are added at one end of the queue and they are removed from the other end. So really the first one to enter the queue will be the first one who leaves the queue. And then there's priority queue, where the thing that gets removed is the smallest thing in the queue, where smallest is defined by some comparator. Okay, so that's the summary there. Can we index sorted sets? No, you cannot. So sorted sets in Java, they do not allow you to access things by index, though we will see a data structure in this course that you could build that would allow that to happen, and it has the same performance as the sorted sets that are in Java, but the sorted sets in Java don't support that. Are stacks implemented using linked lists? Well, we'll see that there's many ways to implement stacks, so that'll come up soon. Okay. What are the advantages and disadvantages? Well, when we're just talking about implementations, usually it's not a question of advantages and disadvantages. It's more of a question of what makes sense. Right. So if you need things kept in a particular order that you define as the order you inserted them, or some order that you're maintaining, then you want a list, because that's the thing that maintains a sequence, that you control the order of things in that sequence. If you don't need that, if you just want to add things and remove things and check if they're there, then you use a set, because that's the operations that are supported. But at this point, when we're just talking about interfaces, which don't talk at all about how things are implemented, really it's, does this thing do what I need it to do? Don't worry whether it's fast enough to do what you want. Just at this point, it's just picking the right thing. And we'll see that there are different implementations with different performance trade-offs, and that's when we can talk about advantages and disadvantages of different implementations. And we'll see that actually some of the implementations implement more than one of these things. Is there any difference between a linked list, under list, and queue? We'll see that shortly. So down here, the second part of the board, these are implementations that we will discuss today, and we'll discuss the advantages and disadvantages of each of them. But for now, let's just finish the last couple of things in the interface hierarchy. So there's the deck, and the deck is, it's kind of funny that they decided to include this as its own thing. A deck is kind of a restricted form of a list, and what do decks support? They support operations add first, add last, remove first, and remove last. And really the way to think about those is, they imagine there's a list hiding inside of them, and there's a first element of the list, and if you add first, then the thing that you add goes before that. If you remove first, well, the first thing is the one that you remove. And at the other end, if you add last, the thing that you add goes at the end of the list. And if you remove last, then you take away the last thing from the list. That's called a deck. Deck is short for double-ended queue. It's a queue that, well, it's a sequence that you can add and remove from either end. And the deck interface, unlike the list interface, that's the only sort of access that you get to this thing. There's operations, I think they're called peek first and peek last, that let you look at the first and last element, but you can't just go and jump into the middle of a deck and look at things in there. If you want to see what's in there, you have to remove a bunch of stuff first. So we don't really think of them as indexed by anything, because you can't access values by index. Although it certainly would be easy to implement a deck using the list add and remove operations, because the list add and remove operations let you specify the indices. And so here you're adding and removing at index 0 in a list, and here you would be adding and removing, well, you'd be removing from index size -1, and you would be adding to index size. Okay. What we're going to call forever, we're going to call this n, and we'll call, which makes this n-1. Okay. So why would you want something that only does these operations? Well, maybe it's simpler and faster if you only have to support these operations. We'll see that that's actually not so true, which is why I thought it's a little bit strange that they decided to include dec as a special thing here, because you can implement a fully general list that supports those things plenty fast. Okay. Are there any data structures that function like a dec but allow you to go in the middle of the sequence? Someone asks. We have done assignments in the past where people implement something that we called a TREC, which we called a triple-ended queue, which does allow you to add and remove efficiently right in the middle, directly in the center. So it's not a standard data structure, but it's one that you can build fairly easily with the things that we learn in this course. In fact, you can build such a thing fairly easily using 2 decs. What's the practical use for a dec? Why does it exist? Well, I know of one algorithm, and we may actually discuss it later. It comes from the field of computational geometry, where it's just it's the right data structure to use to compute something called the convex hull of a chain. Just because the way the algorithm works is it maintains basically a sorted list of the solution so far, and when you want to add something else to the solution, well, adding it removes a bunch of things from the back, or removes a bunch of things from the front, and then adds it to the front or the back. So there are practical applications of it, but more importantly, a dec, of course, gives you a stack if you want to use a stack, and it gives you a queue if you only want to use it as a queue, right? If you want a stack, you just use add first and remove first. That always adds and removes from the same end. And if you want a queue, you add first and you remove last. That gives you the first in, first out queue. So it's kind of a general version of the most general kind of queue type structure. Okay. Is it necessary to have X element in the add first, add last, whereas remove first and remove last don't have it? Yes, because when I want to add something, I have to tell you what it is that I'm adding. So that's why there's an argument X. But if I tell you to remove the first thing, well, I don't get to tell you what to remove. What gets removed is the first thing. It's whatever happened to be there. And the same thing with remove last. So that's why these take an argument and these don't. And the same thing with queues. The add operation in a queue takes an argument. What is the thing that you're adding? The remove operation doesn't take an argument because that's determined by the queuing discipline. Okay. How can we access the data stored in the dec? The only way to access it is through these operations. If you want everything from the dec, you can simply remove it all. It'll come out in order. If you want it in reverse order, you can remove it from the other end. It'll come out in backward order. And remember, a dec is also a kind of collection, and collections support iteration, so you can use a for loop on a dec to access all of the elements in order from first to last. Now, if you only want one of the elements, that's not a particularly efficient way to do things. Does remove first and remove last return the element? Yes, it does. So when we do a bit of programming examples, that the remove operations give you back the value that is removed. Okay. So that takes care of this collection side of the hierarchy. And sitting off beside that, because it's there's no is-a relationship between these things and things over here, are map and sorted map. And if you're observant, you'll notice that map and sorted map sure looks a lot like set and sorted set, and that's because these things are very close together. In fact, we'll see a little bit later, once we look at how these things are implemented, that the same technology is used to implement both of those things. But first, what is a map? So what Java calls a map is what in Python is called a dictionary. Okay, so it maps keys onto values. Okay, so the main operations there are get. You pass this thing a key, and it returns the value associated with that key. And there is put. It takes two arguments, a key and a value, and it associates the value v with the key k. So an example might be something like keys, which are people's names. And values, which are some number associated with this person. So maybe, I don't know, something like ages. And so that's what a map does. It associates with each key, it associates exactly one value. You get to choose the type of keys that you store, and you get to choose the type of values that you store in your map. You can get the value associated with the key, and you can associate a particular value with a key. Okay? But in order to get it, of course, it should already be in there. So here, if I ask to get the key, or get the value associated with Irene, then I'll get an exception because Irene is not in this this particular map. Yeah. Keys need to be unique. Yes. So that's a good point. So let me be really specific here. It maps keys onto values. So it actually maps a set of keys onto values. So I cannot have two keys that are pat, and I can, so really the things that are the keys have to form a set. Set, remember, everything is distinct in a set, so I cannot have two of the same keys. And how would that happen? Well, if I try and put the same key twice, well, all that happens is you're changing the value associated with that key. So if I did a pat put pat, someone says I look younger than 29. Let's say that that's true. If I have this particular map and I put 25 with pat, all that does is change the value. And so you see, actually, there's already a lot in common between a map and a set. In a set, well, there's a set of things that you maintain. You can add and remove things. And, well, a map maintains a set of keys. The only sort of extra thing that it does is with each element of the set that it's maintaining, it associates a value and lets you retrieve that value. And so there's a few other functions that basically have to do with that. Maybe the one that really shows that these things are like sets is there's a remove key function. So put is like the add function for sets, and remove key is like the remove function in sets. The only difference is that there's this extra stuff floating around. And there's a few other ones. For instance, there is contains key. Which you can use sometimes as a guard. If you're not sure if your map has the key k in it, then you first check to see if it contains the key. Then you're allowed to get the value associated with k. So really, these are exactly the things that sets do quickly, but there's this extra sort of value associated with things. Okay, this is an extremely useful data structure. So there are uncountably many applications in which you want to do exactly this. Associate some keys with values. Think of student numbers onto student records, or social insurance numbers onto tax forms, or any number of things, or the other way around, things like putting names back onto difficult to remember things like student numbers. So all of those things work there. So this is an extremely important data structure used all the time. Okay. And then there is sorted map. And what's a sorted map? Well, a sorted map is a map. It supports all the operations that a map supports. But the best way to think of it is it's just a map in which the key set is a sorted set. Okay. So supports all the same things, but now if I do something like iterate over the keys of a sorted map, they will come out in sorted order. And the key set, which actually you can access in a map, what comes out of this is a sorted set, which means you can do range searches and things on the keys. Okay? So it's exactly analogous to the relationship between set and sorted set. So it's actually it's a surjective function, or actually it's just a function. Surjective relation. It's a function, meaning that it's a function from keys onto values, which means you don't have the surjective part means that you don't have a key that maps onto two different values. But you can have two different keys that map onto the same value. For instance, in this example, if you have two people with the same age, then indeed they will both. It's fine to have two people whose age is 25 inside your map. Okay. Good. All right, so that is the interface hierarchy. And remember that the interface hierarchy just defines what operations are supported by the data structure, and in some sense what those operations mean. But we saw even with the queue that the interface doesn't necessarily even totally define what they mean, because for queues, there's different kinds of queues, FIFO queues and priority queues that behave in different ways. In particular, the remove operation behaves differently. Really, technically, in Java, the interface just defines the set of methods that you have that a class implements. In Java, actually, the interface doesn't tell you anything about what those methods do. It just tells you the signatures of those methods. Okay. All right. So what we should do now is take a look a little bit at what are the classes that implement these interfaces. And I think the best place to start is with the two common classes that implement the list interface. And it's important we will look at these in the actual implementations and code and real analysis of how they manage to do these things. But for your assignment, there are some performance characteristics of these two implementations that you need to know in order to avoid doing something bad in your assignment, meaning making an implementation that's too slow. So the first implementation, very commonly used, is the ArrayList. So this is a list implemented using a single array. And this is a fairly natural thing to do, right? So remember, a list has a few operations. The easy ones are get and set. And then there's add and remove. And the list, it's supposed to represent a sequence of elements indexed from 0 So it's supernatural to store that sequence of elements in an array maybe something like this, because then get and set become really easy to implement. So you use the convention that the list element I is stored at index I in the array. So I don't know, let's call that array A. Then you could very easily write sort of naive implementations of at least these two, because get I just becomes return A at I. And set I to the value x set I, the set method in lists actually returns the value that used to be stored there. So it actually takes a couple of lines. It looks like this. You do something like y gets A at I, so save the value that's currently there, then set A at I equal to x, and then return y. Really, really easy stuff. These operations, though, they're a little bit different. They're not things that we maybe typically think of doing on arrays. So, the question, what's the difference between an array list and a normal list? Well, in the context of what we're talking about here, list is just an interface. Tells you nothing about how it's implemented. ArrayList is an implementation of the list interface that happens to use an array. So list is a generic thing that could be an array list or a linked list or some other data structure that implements the list interface. ArrayList is one particular implementation of this thing. So, does anybody see difficulties that might come when we try and add something at a particular location in an array list? So yeah, the array will run out of space. Indeed, that is a problem, because if you remember arrays, so in Java, the way you allocate an array is to say something like A is equal to new, I don't know, the type of thing that you want to store, maybe if it's an array of integers, and you specify some length, some integer which tells you the length of the array. So for example, this array here would have been allocated with 9 as its length, elements indexed 0 through 8. And then arrays don't grow. That's it. You allocate an array of a specific size, and then that's the size of the array forever. Now, the add operation expects to be able to add something new to your array list and keep everything that's already there. So, so that's a problem that at some point you're going to run out of space. A trick that's used that the ArrayList implementation does, and it's kind of already illustrated here, is that in general the array that's used to implement the list will usually be larger than the actual number of elements in the list. Okay. So that problem of running out of size running out of the array not being big enough doesn't happen every time you try to add something. It happens less frequently than that. And one of the first lessons that we'll learn, the sort of first non-trivial things we'll learn, is how that can be done in a way that actually doesn't affect performance badly at all. So even though sometimes you run out of space in your array and you have to make a bigger one, if you do this carefully, then you'll still have an implementation where the time that you spend copying stuff from small arrays into larger arrays doesn't add up to much in the big scheme of things. So that's one issue. Any other issues? So let's pretend for a moment that arrays can, when we want them to, they can get bigger, because we'll see a technique that allows us to do that efficiently. But what else is kind of not impossible to deal with, but might be slow to deal with? Shifting items back. Yes. So this add operation, for example, and this remove operation we'll see in a second, it tells you the index that you're supposed to add the thing at. So for example, if I say, in this particular one, if I say add at position 3 the value p, then when I'm done, p is going to be there at position 3. But before I can do that, I have to make room for it. And to make room for p at position 3, that means q has to go to position 4. But there's already something at position 4. There's r. And so to make room for q, I have to move r to position 5, but there's already something there. So then t has to go from position 5 to position 6, and then v has to go from position 6 to position 7. The way this is implemented is sort of exactly what you would think. When I want to insert something at position I start at the end of the array and move things over by 1. And finally, that frees up the space for the thing that I want to add, and I put it there. Okay. So that's doable, assuming the array has one extra position, one free position available in it, but it can be slow, right? I mean, depending on the length of your list and the value I that you choose, the number of things that have to move out of the way is n minus I. And here, that was, before it was 9, and we were adding at position 3, so I guess it's n, oh no, there were 7 things before, we're adding at position 3, so 4 things had to move out of the way. But you can imagine that, well, maybe your list has length 1 million, you want to add at position 500,000, so now 500,000 things have to be shifted out of the way. And indeed, when you add at position 0, that is the worst thing that you can do, because then everything has to move over and make space for this newly added element. Okay. This is important. This is an important thing to know about array lists, is that this operation, the time that it takes, depends on the value of I and the length of the list. And I'll write this in big O notation. This takes 1 plus n minus I time. Okay, so we'll revisit big O notation a bit formally, more formally later, but for now just think of this as something that hides constants that depend on various things like how fast your computer is and other things, and only gives upper bounds. But in this case, there's some amount of work you have to do to add something. So even if you want to add at the very end, there's some constant amount of work that you have to do. Could be just setting the value to of that array location takes some amount of time. But in addition to that constant amount of time, there's n minus I things that have to be shifted and moved out of the way. And each one of those, is moving one piece of memory. In Java, it's actually changing one pointer, and that has to happen n minus I times. So if n is big and I is small, then this can be a lot of time. So this is the time for shifting, and this is the time for everything else. So this add operation can be slow or fast, but really it's only fast when I is very close to the size of the array. And remember, the size, not the size of the array, the size of the list. And the size is this thing that we're always going to call n. I'll keep repeating that for the next little while. The number of elements in your list. If I is much smaller than that, then a bunch of things have to move out of the way. That's very slow. What's the one for? Yeah, the one is for this other stuff. Everything but the shifting. I'll say everything else. And why do I need a 1 there? Well, because I can have I be equal to n. That's what happens when you add at the end of a list. You add at position n, because it's 1 more than the last index of your list, in which case n minus I is 0, and the code doesn't run in 0 time. It still has to do something. Okay. That clear? All right. And just to note, the value of I here in the add operation can be anything from 0 up to n. N is what happens when you want to add to beyond the end of the list to make the new thing the end of the list. But in these functions, the value of I can only be from 0 up to n minus 1, because otherwise you're trying to get or set the value of some element that is not present in the list. Right. So here, for example, in this list, right now, n is equal to 8. I can add something at position 8, but I can't access the thing at position 8 because there's nothing there. We'll have to get used to working with sort of remembering that when you have n things, they're indexed 0 through n minus 1, but the number of places you can add stuff is actually n. You can add it before everything, or in between the first and second, and so on. And then there's that extra place, which is after everything. Okay. And of course, the remove operation, this also can only be 0 through n minus 1. And it suffers from exactly the same problem as the add operation, because now if I decide to do something like remove 0, then yeah, that means A is going to go away, so I'll pluck it out and return it, but something has to take its place. And what has to take its place is B, then something has to take B's place, which is Z, and so on. And so the remove operation is implemented exactly the way you would expect it to be. You first store the value of A because you're going to need to return it. Store that in some variable called, let's say, Y, and then start your shifting where you copy B to position 0. And then whatever's at position 2 to position 1. And whatever's at position 3 to position 2. Whatever's at position 4 to position 3. And so on. Oops, sorry, I got that wrong. T, and then V goes there. Like so. And then the value of N drops. Now it's no longer 8. N is 7. So here, an array list, we can almost work out the implementation ourselves quite easily. The only thing that I'm hiding for you, because it's sort of one of the first lessons we'll do once we get past how the Java collections framework works, is how we can do this growing the array efficiently, or shrinking the array efficiently also, so that if we add a bunch of things to a list that creates a huge array, and then we decide to delete most of them, we shouldn't keep that huge array hanging around. It's using up memory. We should be nice and give that back to other processes. Okay. So any questions about that? When we add Addix, do we get true as the return value if we were successful? I don't remember. I think Addix has a void, so no return value. But I guess in any case, because I've never looked at it, it's almost never useful to return anything from there, because if you weren't successful, then it's going to throw an exception. Maybe it ran out of memory, or maybe the value of I was invalid, like you tried to add at some position larger than n, or even a negative index. But as long as it doesn't throw an exception, I don't know what useful return value could come from addix. Will there be lectures where I'm coding? Yes. So possibly, in fact, probably the next lecture, I will sit down and code, and we'll actually use some of these things to demonstrate how they work, and because there's some syntax issues that I don't want you guys to get hung up on. And actually, when that happens, we're going to have to do it some other way, because YouTube, I'm not going to turn around and put my computer in front of a camera. We'll use something like either Zoom or Big Blue Button to do those classes, and as well, I will do a screencast that so that later you can watch those on YouTube. Okay. I will generally send out an email through the forum before those classes if there's some weird thing that you need to do to watch, or you'll go to the usual place you go to find these streams and see that there's a pointer to something else you should do. But probably it'll be through See You Learn, because those it's sort of popular these days to bomb those kinds of meetings. So I don't want that link public at all. We saw already just the random people who show up from videos being recommended on YouTube can cause grief. Okay, a little story about this, and that maybe you can keep in mind as class goes on. This shifting is slow and painful, and it always reminds me of a time when I was traveling through the Montreal airport on the way to the United States, and I was one of the people chosen for some extra security check by the US immigration officials. So I had to go to some room and sit in there with a whole bunch of people, and you have to give up your passport when you go there. And they implement a queue. In fact, they really implement a first in, first out queue using your passport. So there's a whole wall of little boxes like this. Actually, they were vertical, but easier if I draw them horizontally. And there's a bunch of, each one of them is holding a passport in it. Or at least starting from the beginning, each one is holding a passport in it. And then you come along and they take you in, the security person takes your passport, and they put it there. Okay. And, you know, at some point, somebody comes from the room where they've been searched or whatever was done to them in that room, which means the room is available to take the next person. So this is the funny part. The security person, actually I think there's one person, this was their entire job. They take out this passport, they open it, and they call your name, and then someone takes you to the room for your discussion. But then this person who's doing this passport's now gone from here. This person picks up this passport and puts it in here. And then they pick up this passport and put it in here. And then they pick up this passport and put it in here. And so on. Every time somebody gets called in for this security check, this individual has to move n-1 passports left by one position. This is this person's job. So we'll see soon enough that actually if those people knew a little bit of computer science, they could have come up with a much more efficient way of doing this, where that poor fellow would only have to take out a passport, one passport, and there still wouldn't be any confusion about who's next. Things would still come out in the right order. In fact, you think about solving that problem yourself, and you will probably come up with the standard implementation of a deck using an array. If you just think about what that security guard's doing and what they could have done differently. Okay. So that's ArrayList, and the key thing to remember is that in an ArrayList, adding and removing is only fast if you're adding and removing at the end of the list. Now, there is a second implementation of a list that's called a linked list. And in technical terms, the linked list in Java, this always comes up, especially during exams. The linked list in the Java collections framework is what people call a doubly linked list. So there you don't use an array. What happens is each element in your list is contained in a little object called a node. So if you have a list that contains a bunch of things, that list contains a bunch of nodes. And what's a node? Well, a node is a really simple object, so we're talking about a linked list here, that stores a data item and two pointers. Those pointers are pointers to other nodes, or maybe not even other nodes, maybe pointers to the same node. But in general, the picture looks like this. And if you don't like that I'm using the word pointer, if you really are a Java fanatic, you can think of the word reference instead. But pointers and references are really the same thing. Okay, so these things are linked together this way. So remember, the list items have indices 0, 1, 2, 3, 4. And the node for the item at position 0 has a pointer to the node for the item at position 1, and the node for the item at position 1 has a pointer to the node for the item at position 2, and 3 to 4, and 2 to 3, and 3 to 4, and so on. And each one has two pointers to the node that comes after it, and another pointer to the node that comes before it. So maybe these are called the next pointers to the next node, and the previous pointers to the previous nodes. And this is why this particular thing is called a doubly linked list, because there's sort of double pointers between two nodes. There's a pointer going in this direction and a pointer going in this direction. Okay. And I don't think the Java collections framework does this, but when we study linked lists, we'll see that there's the cleanest way to do this is to actually introduce an extra node, which is not an element of the list, but it's a node that comes after the last element, but it also comes before the first element. It's just a handy thing to have, actually. Otherwise, we run into trouble when we do things like delete the last element of the list, or we delete the first element. We can run into extra cases. This gets rid of those. All right. So remember, the list interface has to support some operations. Get I, set IX, add IX, and remove I. And remember, objects in Java, right? When you create a class, you say what its instance variables are, but those are a constant number. There's a fixed number of those instance variables. So you can't have instance variables for every node, right? An object has a fixed size with some space reserved in it for some variables. And the thing that is reserved is this thing here. I'll call it a dummy. This is what's in the linked list object. It has this one node called the dummy, or possibly it has just two references called first and last if it doesn't want to use this dummy node technique. But when I pass you a linked list, what you get is this thing. Okay. So what's the issue now? If I want to implement get I, what happens? So for instance, if I want to do something like get 2 in this example, what do I have to do? Yep. So you have to iterate, because the list, the object, does not have the node 2 inside it as an instance variable. The only way it can get to it is by starting from the first node, or the node that's even before the first node, and walking forward. Or maybe starting from the last node and walking backward. Okay. So in this case, it actually doesn't matter which one it does, but there will be a for loop in the getI method that starts at position, you might call it -1, and then follows the pointer to get to position 0, and then it follows the pointer to get to position 1, and then it follows the pointer to get to position 2, and then finally it can return the value stored at that node. Okay? And the doubly linked list is a little bit clever about this, because although it doesn't matter when I ask you to get the node at position 2, if I ask you to get the node at position 0, then I think it's pretty clear that the best way to do that is to start at the dummy, follow the next pointer, and you immediately reach position 0. On the other hand, if I want to get the node at position 4, then it doesn't make sense to start at the dummy and follow next pointers, because then I have to follow 1, 2, 3, wait a second, 1, 2, 3, 4, 5 pointers, right? I'm starting at position -1 and going all the way up to position 4. That's a difference of 5. Instead, it makes a lot more sense for me to go in the other direction, follow the previous pointers from the dummy node. That takes me immediately to position 4, and I'm done. Okay? So, in a doubly linked list, this getI method, unlike in an array list, already this is not obviously fast, right? Does the dummy node actually exist? In the implementation that we'll study, it does exist. Some implementations just use the separate first and last pointer. I consider those to be actually unnecessarily complicated implementations. A dummy node makes things a lot easier. Okay, so what does that mean about the running time of this getI method? Well, so in addition to the dummy node, the list should remember the value of n, how many elements are stored in it. And then it can look at I and n. So when you ask me to get node I look at those two things, and I and n, and I decide whether it's faster to go forward from the beginning, so that happens if I is less than or equal to n over 2, or whether it's faster to go backwards from the end, and that happens when I is bigger than n over 2. But then the running time of this thing becomes O of 1 plus the minimum. If I have to go forward, then I do something like I take I steps. And if I have to go backwards, I take something like n minus I steps. It's actually n minus I minus 1. but the big O notation hides those little things. So this is the running time of the get method in a doubly linked list. It's basically how far the value is from the nearest end of your list. Okay? Is that clear? This is important to understand. So the get operation doesn't take constant time like it does in an array list. In an array list, you just go to the array location and it's done. So this is really the only thing to know about linked lists, because all these other operations have the same issue. All of them require you to get to the node that contains list item I in order to do what you want to do. And that means they're going to have this in their running time, a loop that goes from the beginning forward or goes from the end backward. So, any question there? So what is the advantage of using a linked list versus an array list? We'll answer that in about 2 seconds. But first, I think we can see now the set IX method is almost the same. If I want to set the item at position 3 to the value x, then I first have to get to the node that contains it. In this case, it's faster to go this way, which is what the algorithm will do. And once I get to that node, then again, I save the value of whatever happens to be there already so I can return it. Then I change the value that's stored there and I return the old value. Okay. So it's also going to have exactly the same running time. Okay. Good. Now what about the add operation? Well, let's try that here. Let's try and do add 3 R. So in that case, I still, in order to add it, I'm going to have to somehow get to this this thing here, 3. And so I'll still have to follow pointers. In this case, it's still faster to go backwards. Since I'm adding something, I'm going to need a new node to add. So I have to make some new node that contains the thing that I want to add. And now once I've reached this node, it's time for me to very carefully and in just the right order start changing pointers so that I finish. There's 4 pointers to change, but once you've changed them all, you finish with this picture. And what does that do to the indices? Well, in my picture, I wrote down these indices, but they're not actually stored anywhere in the implementation. They were just there for us to keep track of what the numbers were of things in the list. So by changing these pointers so that this node gets spliced in, what actually happens is implicitly the indices change. I didn't have to do any work to change those indices other than to splice this thing in. It took me some time to maybe find where I needed to splice it in, but other than once I got there, I only had to do splice it in and all the indices changed. Okay, but still, yeah, it's still going to be the same story. Add IX has to go and find the place to insert the new element, and then it has to do the insertion. So there's this variable part that depends on the values of I and n, and then there's a little bit of work changing 4 pointers that you have to do no matter what. And remove, I think we can already see how that works. If I wanted to do something like remove 1, then I would start from the dummy. It's faster. Right now the value of n is 6. Since I'm only trying to get to 1 and n is 6, it's faster to go forward. So you do that, it takes 2 steps. And now I want to remove this thing. And how do I remove it? Well, again, that's just changing 4 pointers. Very carefully, about being very careful with the order that you change them. You want to finish in a state where the data structure looks like this. This one points to that one. This one points to that one. And nobody points to that one. It's gone. It's not in the list anymore. And again, that implicitly changes the indices. This one is not in the list anymore. It doesn't even have an index. But the 2 now is at position 1, because if I take a step to 0 and then a step to this, I get to there. And this is position 2. This is position 3. And this is position 4. Okay. All right, so now I can finally answer the question that someone asked. What's the advantage of a linked list versus an array list? Well, remember, in the array list, these operations had a running time that was O of 1 plus n minus I. Because I had to shift n minus I elements. In a linked list, they have 1 plus the minimum of I and n minus I. This was very slow when I equals 0. When I equals 0, then this is 1 plus n. Every element in the list has to be shifted. Here, when I equals 0, this is just constant time. Okay? So, in a linked list, you pay extra for get and set, especially if you want to get and set near the middle of the list. But if you want to do anything near the ends of the list, it's actually fast. So in particular, if you're working at index 0 or you're working at index n or n minus 1, then everything runs in constant time. In particular, working at index 0, adding and removing things, is something that's super slow in an array list, but super fast in a linked list. Okay. Questions about that? Yeah, so remove basically unlinks nodes rather than delete them, because in Java, remember, there isn't really a notion of deleting things. Java is a garbage collected language. All you need to do to delete something or have it so that it's eventually deleted is stop having any references to it. And in this case, this thing gets unlinked. Once the function returns, there's no more references to this node. At some point, the Java garbage collector will run and clean up the memory that's associated with this thing. So in a language like C or C++, where you explicitly allocate and deallocate memory, you would call free or delete for getting rid of this node. But in Java, that just changing the pointers is sufficient. Okay. All right. So now, actually, we can see a few things quickly. we have these two implementations of list. ArrayList is great if you want random access to values without adding or removing. Linked list doesn't give you fast random access throughout the list, but it's very fast for adding and removing at either end. And so here we can see a couple of things. Queue implementation, one of the queue implementations is as a linked list. Why? Because a queue adds things at one end, a FIFO queue adds things at one end and removes them from the other end. Linked lists do that really well. So that's why a linked list also implements the queue interface. It's just a couple of extra methods. In fact, it's not even, because the list interface includes an add method that adds at the end, and the remove method takes no arguments. In this case, it just removes the 0th item from the list. So those operations take constant time on a linked list. You could not do that with an array list, at least not the way the array list is implemented now. Because that remove operation, removing the 0th item, would require shifting everything over. Okay. Here's another one, deck. Well, what's a deck? A deck is this thing that's kind of like a list, but you're only allowed to add and remove at the front and the back. But those are exactly the things that a linked list can do very quickly. Adding at position 0, removing from position 0, adding from at position n, or removing from position n-1. Those are the things that linked lists can do quickly, which is why linked list also implements the deck interface, just because it can. Okay. There are a couple of other implementations of these. Well, another implementation of the deck interface, which I will just briefly mention because it sort of solves the problem that that these American customs agents have in the following way, and we'll study this in greater detail later. So you can also implement a deck using an array, and the trick is kind of simple. You store the elements of your deck in an array. But you remember two other things. Normally in an array list, the stuff you're storing starts at position 0. But there's no reason for that. You could instead just keep an extra variable that says, no, I don't always want to start at position 0. I'll keep a variable j that tells me where the data, the first item in my list is. So this is item 0, this is 1, 2, 3, 4, 5. Here would be 6, 7, 8, 9. And you keep another variable which is n, which is the number of items. In this case it's 1, 2, 3, 4, 5, 6. And now actually you see that with those two pieces of information, if I want to get something, although a deck doesn't need to get things, it only needs to add and remove at the ends, but I could even get a particular index because the thing at index I is just at position j plus I in the array, being a little bit careful here. But for adding at the end, adding at the beginning, or adding at the end, it's quite easy, right? If I want to remove first, so I want to remove the first thing in this deck, that's easy. I just increase the value of j, And maybe to be nice to the garbage collector, I will put a null there. And just increasing the value of j implicitly changes all of those indices. Right now, this is the thing at position 0, 1, 2, 3, 4, and so on. And if I want to add first, well, then I can just back off the value of j by 1 and put the new item that I want to add there. And adding and removing at the end is kind of the same as before. Removing at the end just means you have to decrease the value of n and maybe take away the item that was, null out the item that was there. And adding at the end is increasing the value of n and putting a new thing there. Okay. And that all works fine as long as you don't run off this end or run off that end. But we've seen already that even with ArrayList, there's a problem of running off the end. And I kind of waved my hands and said there's a technique for handling that, and we'll see that technique. Well, we'll see two techniques for handling that with array decks. But that's the other implementation of a deck. Okay, so I think that's it. That's it for time today. Does anybody have any questions for me? I can take 5 minutes to answer questions. Where are the practice problems located? What do you mean by practice problems? Yeah, no, I've tried OBS, so two things. I don't really have practice problems, but we have assignment questions. They're on the course webpage, so you can look at the assignment, and I encourage you to do so, because it's now time to start thinking about what are the structures, the interfaces and implementations you'll use to solve those problems. And yes, I am aware of that OBS works for casting a screen on YouTube. I haven't had great luck using it, although maybe for screencasts I don't care. My problem was the software encoder was actually not very good at getting a good frame rate. But if I'm just casting a screen and not a video, then maybe that's okay. I may try that out, and then we can just do everything on YouTube. Can we submit to the grading server multiple times until you get correct? Yes, you can submit as often as you like. The only constraint is that there is a 5-minute delay between two consecutive submissions. The reason for that is twofold. One is, as the deadline approaches, the submission server can get too busy otherwise, and it just stops responding because too many people are repeatedly submitting. But there's another reason to not allow that, which is I would like you not to use the submission server as a way of doing programming by random change, where something doesn't work, you make a random change, you submit it without really knowing whether it's going to help or not. You make a random change, you submit it to the server and see if your grade gets better or worse. And if it's worse, back it off. And if it's better, great. I would like you to at least spend 5 minutes thinking about the change that you need to make in order to fix something, rather than just using the server as a oracle for these random changes. And I do that from experience, because I've had times in the past where students would not even compile their own code locally. They would just submit code to the server, because the server compiles it for you, which seems like a terrible waste of resources and not the point of the course. You should think. Other questions? Given a linked list, index 0 to 5 will get 4, start from 5, or 0, it'll start from 5 because it'll have to take one step back from the dummy node to get to position 5, and then another step back from 5 to get to 4. That's only 2 steps. If it went the other way, it has to go one step from the dummy node to 0, one step to the 0 to 1, one step from 1 to 2. It would have to take 5 steps to go in the other direction. Submitting assignments as a single PDF. There are no PDF submissions in this class. It's code that you're submitting. You're probably confused with the other course that I'm teaching, 2804. There's no link for the big blue button yet. No, because I'm still working on trying to get somebody from I don't know, instructional services or whoever manages this thing to create a merge of both sections of this course, because Big Blue Button limits the participants to people who are enrolled in this section. Now the problem for us, the problem with that is, well, there's 2 sections for this course. We have a total of like 12 or 13 TAs, and I don't think, I think it should be okay for people in my section to talk with the TAs from the other section, since we're doing the same assignments, same exams, same material. So I'm still waiting on them to do that for me, so we can get it. But by Monday there will be a link to a Big Blue Button, hopefully, that allows you to access any TA's TA hours. Oh, is there a reference to a PDF on the 2402 page? If so, I'll get rid of it. Yes, linked list get will do the calculation, which is checking whether which is bigger, I or n minus I, and do the right thing. Do whichever one is faster. What's the difference for queues linked list and deck linked list? Nothing. A deck does all of the operations, adding and removing at either end. A queue only does 2 of those operations, adding at one end and removing from the other, but there's no difference, just that they have different names. Can we create an IntelliJ project and copy-paste the Notepad codes in different Java classes and then try running it? I wouldn't recommend it. I hope at least IntelliJ has a way of importing existing code as a project, not having you have to open 10 separate files and copy and paste things and rename them. For sure that's going to break something, and then your code won't compile on the server. That's the kind of thing you should post a question about on the forum. Somebody who uses IntelliJ and knows it will tell you how to do that. Okay, good. All right, so we'll call it quits for today. This video will be replayable immediately if anyone showed up late, and there will be a better quality version of it posted in about overnight sometime. All right, thanks, bye.